So the goal of today's lab is to see the component colors of any individual ink color. So you're going to be doing different inks, preferably felt tip pens, and the colors are not necessarily going to be single component colors. Some might be a mixture of colors, like for instance, that purple is red and blue. But what about black? Okay, so you're going to be testing different ink colors. You probably want to choose colors that have potentially a mixture, so of different components. So I have an example. This is from the lab procedure of yellow ink. Okay, so the starting point, which you would mark at 1.50 centimeters in pencil. This would be this line straight across that was marked in pencil. This is in the lab procedure. And then you have added also the finish line. That finish line, also in pencil, is at 8.50 centimeters. Okay, so you've written two horizontal lines across, you've drawn two horizontal lines across your chromatography paper strip. So then you've added a dot of color. Okay, so this one is going to be yellow. Okay, so this is the starting point. Then there's the attachment of the chromatography paper strip to a pencil, and you're going to suspend it into a cup and then have water at the bottom. All that's described in the experimental procedure slides, as well as in the experimental procedure steps in the lab procedure. So this is the yellow ink, where you have put a dot of ink on that starting point. Okay, so that you're using the pen. You're using the yellow ink pen, and that's the sample to be tested. So the samples that are tested are placed directly on the stationary phase. So the chromatography paper is the stationary phase. And what happens is that the experiment goes into action when you drop this stationary phase with the sample into the mobile phase. So the samples tested are placed on the stationary phase. That's the chromatography paper. So you could also call that the filter paper. Or you could use coffee filters, I mentioned. So when you then put this into water, that's the mobile phase. The mobile phase, as the name implies, moves. Okay, so this moves and causes the elution process. And what it does is it moves up. So the water moves up. It moves up the filter paper. It's drawn up by capillary action. And as it moves up, it causes the ink's components to separate. And that will be true if the ink is made out of different components. Okay, so for this yellow pen though, let's say that the water moves up, and this is called the solvent front, where the water ends up. Okay, so this is something that you want to get to this 8.50 centimeters, but for many of you guys, including me in my examples, the water will continue to move even after you take it out of the cup because of the same capillary action. So you'll have to measure this solvent front. This will be measured after the experiment, and it is the distance that this water moved. So it's the total distance that the water traveled, and this is up. Okay, and this is up from the starting point. So it's going to actually move a little bit past that 8.50 centimeters after you take it out while it's drying. So as the water moves, there are a couple things that happen. So if your ink is separate components, it'll split into different spots of color. Okay, if your ink is a single component, this would be an example of yellow. It moves up to here, and it's just one spot. at the end of the experiment. You can see that it has not moved all the way up with the mobile phase, and so that means it was not 100% attracted to the mobile phase. It didn't move with the water completely to the end. It stuck a little bit behind. So there was some attraction to the water, there was some attraction to the mobile phase, and there was some attraction to the stationary phase. It still stuck to the paper. So there's the spots will travel a certain distance depending on their relative attraction to the mobile phase versus to the stationary phase, and it's going to be something in between. Okay, so literally in between where it could start from if it were 100% attracted to the paper, or where it could end if it were 100% attracted to the water. Okay, so there's an interplay between its attractions to either the mobile phase or the stationary phase, to either the water or the paper. So what you have here is the distance traveled by the sample, the component sample. So this is the D value, and this is also measured after the experiment. The D value is the distance traveled by any individual component. So those are individual spots on the chromatography paper. Okay, so this is called the D value compared to the F value, which is the total distance traveled by the mobile phase, the water. Now you should notice that both of these start not at the 0 point. They start here at the starting point. That's where the experiment started, and this is where the experiment ends. So in order to calculate what's called the retention factor, you are taking those measured values and putting them into this equation where the D value is the distance the spot traveled in centimeters. The F value is the distance that the water traveled, also in centimeters. So the value for RF actually has no units because the centimeters cancel out. Centimeters divided by centimeters will cancel out in that fraction D over F.